And so we were discussing about flow measurements, and I told you there are a number of flow measuring devices based on different principles uh, available here. So I was discussing first of all the hot wire anemometer. The hot wire anemometer, I was also telling that there could be two types. One is a constant current type, where you have, say, suppose a constant current source I there, and this is your thin wire. This is your heart A there. This is the thin wire which represents the sensor and which is exposed to the velocity V there. That means this is the thin wire which is exposed to the velocity V there. And so, as the current is passing through it, there would be some heat generation. There would be some heat generation. And at the same time, there would be some heat dissipation. And this, if we recall, in the steady state condition, I square into RT, that is equal to H into A into TT minus TF, where this is the heat generation, this is the heat transfer coefficient, this is the area, the temperature of the filament, I mean, that is a wear, and temperature of the surroundings, that is the fluid there. And this one, H, is a function of the velocity V there. This is represented, this is a function of the velocity V there. So as a result, what will happen if the velocity increases, there would be more heat dissipation, and as a result, the temperature of the filament, or the what we call it a sensor, will decrease. And as the temperature decreases, its resistance will also decrease. And as a result, because it's a metallic filament, and a result, if we measure the voltage across these 2 points there, suppose I call it E0, that will be a function of the velocity there. And I kept the constant current constant only, we have shown only to simplify the equations, otherwise it could be the other things also. So that is called a constant current type there. Another part which is a little bit more complex, but involving uh, has got certain advantages compared to the constant current time. But I am not going to discuss in detail, maybe in the next semester, while we discuss the feedback type instruments, it would be taken up, because this involves the constant temperature type, involves feedback principle. What is it? Let us consider this is our sensor, that is the filament, and it is exposed to the velocity V. Okay, I can put some resistance also there. So, it's basically a Wheatstone bridge there. But we try to operate the Wheatstone bridge always under balance condition. So suppose we first use this Wheatstone bridge. So these three resistances are fixed and they do not change their resistance with temperature or the current flowing it. But this being a tungsten filament, basically a tungsten filament, a very small wear of resistance, maybe 5 ohm or like this there, uh, it is sensitive to the uh, current or the temperature of the, its resistance changes with the temperature like this. So let us find it out that I try to make the bridge balanced at when V is equal to, say suppose the bridge is balanced. So if the V is equal to 0, the bridge is made balanced. Now say when V is greater than 0, that means the velocity is more than 0. That means there is a fluid flow there. And what will happen? If the fluid flow is there, that will cause the more cooling, and as a result here, the temperature of this one will go down. And as the temperature goes down, what will happen? The resistance will also change, and as a result, the bridge becomes balanced. Becomes unbalanced. So what we say is that whenever the V is greater than 0, there will be more cooling, and as a result their resistance will become less and than the other one. So at a result, what will happen? That the bridge will become unbalanced. Now suppose I depute some person there. I depute some person who will always see and monitor what is the voltage there. So he will see that as the voltage, uh, as the unbalanced voltage increases, that means because the velocity increases there. His job will be to try to bring in the bridge balance. His job will be trying to bring the bridge balance. So what we can do is that this current, say suppose I, and this one I call it IH, say, hardware anemometer current. So his job will be that to restore the bridge to the balance there. By looking at the unbalanced voltage, he will try to restore the bridge to be balanced condition. Obviously, the first one what we always try is to vary the resistances and other resistances here. But instead of that one, what is done is that we vary this resistance. We vary the battery voltage across the bridge there. Or rather we can say we vary the current flowing through the bridge there. As the I increases, what will happen? So suppose if I see the bridge is become balanced, my job will be to vary the resistance so that the I increases. If the I increases, what will happen? The IH, the current through the hot wire filament will also increases. So what is happening is that the I is increased, then externally. So if I is increasing, then IH is also increased. And again, if the IH is increasing, again what is there? The heat generation will also increase. And as the heat generation will be increasing, so the temperature of the filament will increase, and the resistance will be restored back. So what is our job is then the bridge is balanced again. So what does it mean? It means that whenever I have brought it back to the valence position, that means the temperature, the resistance of the filament is back to the no flow condition, even with the flow there. Or we can say the temperature of the filament will remain the same. That means it will be the constant or like this there. So that's why the name is constant temperature type, like this there. So what will be there at present we can think of, I put some person here, they put it there. You will see once the voltage is unbalanced voltage with the change in velocity, the unbalanced voltage is increased. He will do it is that he will increase the current by varying this resistance, and so that the IH is increased, and see the temperature goes back to the original one, and the E0 is back to the E0 is back to the balance condition. So in that case, we call it a constant temperature time. But definitely we will see, should we keep a person posted to do the variation all the time? Definitely not. It is, but it can be done, nicely done by using a feedback. That means once we see there is an unbalanced voltage, the unbalanced voltage is sensed and amplified by an amplifier. And that amplifier output voltage drives the supply voltage to it. So it would be a closed loop scenario where you can vary the area. So it may be something like this there. Say using a feedback. So what I can do is that you put some amplifier here, that is the unbalanced voltage is amplified there, and the amplifier output is two terminals of the, not a single terminal with a ground, but two terminals of the amplifier there, and these two terminals are fed to or we can say, okay, fed to some amplifier, and the amplifier output is again exciting the bridge. So as the bridge becomes unbalanced, the voltage increases. This voltage across the supply of the bridge is also increased by properly choosing the amplifier gain, and it is uh, brought back to the balance condition. It's brought back to the balance condition, and at balance, while we say it is a constant temperature device, and at balance we note what is the current through this one and I through this one by a small resistance and a supply voltage there. So this is a uh, this is the constant temperature device, which is called, you can see it is also a feedback type instruments. In fact, we will see it afterwards. Feedback is not only used for control, but feedback is also used for many of the instrumentation purposes, for improving the performance there. So now you may question that what is the improvement, why we go for this one. If we say that this one, this software at anemometer is a normally is a constant current type, is that what we can say is that the time constant, we can say linearized time constant, because it is a non-linear device, but it could be this one can be brought to a first order system, and the first order system time constant is approximately is equal to 5 millisecond. We can say that it is quite fast, it is a 5 millisecond here. And as a result, we can also see that what is the turbulence of the air, it can measure. But in this case, it is interesting to see and to hear there. I just try to see, I mean, all the things are there in the Bernoullis book. Those who are interested, you can go through it. But one thing is interesting is that, so it is in open loop. And the time constant in this case, for this constant temperature type, in closed loop, what is expected? Time constant will increase or decrease? What is expected? The time constant, should it increase or decrease? If we recall that the effect of feedback in any system there, you may see, if we recall the first courses, I mean first lectures in the control theory, that, or you can go through Ogata or Kuo's very classical books there. You can see that the effect of feedback is one of the effect of feedback is that decrease in gain and increase in bandwidth. It is a bandwidth is increased, and if it is a bandwidth is increased, means the effective time constant decreases. In this case, the effective time constant, it would be approximately in the in closed loop is approximately 17 microseconds. Just you can see, though it looks to be more cumbersome and like this there, in a closed loop instrument here there, the same thing, if the same instrument, same sensor, if we incorporate in closed loop, we call it a constant temperature type, that can become faster there. And if it is faster, that means more turbulence, high frequency turbulence, it can measure. And that's why the constant temperature type is better than the constant current type. That is a area. So further details, I request you to go through the Bernoullis book, and possibly who will teach in the next semester while discussing the feedback type instruments, he will go through it more details in it there. So the crux of the thing is that the constant current type is an open loop device, but constant temperature type is a closed loop mechanism for the measurement of the velocity, and the constant temperature type is faster in response. In that case, the turbulence of the air velocity or like this at high frequency, it can measure if compared to the better compared to the open loop type and or constant current type. So I didn't go through the details of it, but this is the crux of this one. Is it okay? Any question? If it is not, then we will go for the next topic. Now I will go for the most popular type of flow measuring device and area. They call it an obstruction type flow meter. You must have in the lab, some of you must have done the area that is orifice meter, venturi meter, turbine type, rotameter. These are all basically the obstruction type flow meter because they work on the same principle there. So before going to that one, we will find you may recall that the types of flow. This could be laminar or it could be turbulent. So the laminar flow is basically very calm and quiet like this there, where there is no turbulence. I'm saying it here. There. The example is that, say, suppose if you allow oil to pass over a surface or like this, it would be what we call it basically due to the high viscosity of the oil. So basically, the oil will move layer after layer or like this there without creating much of turbulence there. On the other hand, if water flows at very high speed or like this, there would be always a turbulence there, and that's why we'll see get some sound or like this there. In fact, if you open up your tap or anything, there is always, or any river the flowing through it, it's always there is always some turbulence in it. And we decide whether the flow is laminar or turbulent. So laminar is mostly it is a viscous flow, that means where the friction is a predominant one, while the turbulent flow where the viscosity, because water, it is mainly for water or like this, the viscosity is less and it is so the friction component of the flow is also less there. How do you decide whether the flow rate is laminar or turbulent? It is given by this Reynolds number. I think you are all familiar. It is known as RD is equal to rho VD divided by mu. Okay, I will call it mu here. So where rho is the density, V is the velocity, D is the pipe diameter. I am just considering a flow through a pipeline there, and mu is the viscosity. So if it is flow is viscous, mu is high, Reynolds number will be decreasing there. And at the same time, if the velocity is more, Reynolds number will increase. And we normally say that if for water Reynolds number is less than 2000, we say flow is laminar. On the other hand, if the Reynolds number is greater than 10,000, we say the flow is turbulent. So we can say that this is a between 2000 and 10,000, that we call it a transition zone, which is neither fully laminar nor fully turbulent. But if it is more than 10,000 Reynolds number, we always assume, or rather we can confidently say that the flow is turbulent. Flow is turbulent. So, we are assuming in this case the assumptions, and normally the industrial situation always go for this turbulence of turbulent flow there. So, in this case, the assumptions while you go for further analysis, one is frictionless flow, that means turbulent flow. While you go for the fluid properties and there, we are neglecting any uh, that is a friction in the path there. Because if it is turbulent, the friction can be neglected. And second thing is that it is incompressible fluid. That means it's a liquid, because gaseous flow, because this flow measurement could be for gas, always also for liquid also there. In this case, we are considering only for the liquid area. So these are the two basic assumptions that we are assuming for the further analysis. We are assuming that it is a frictionless flow, and second thing, it's a incompressible flow there. Now let us try to go further. How to measure the flow rate? Let us start with the basic principle. Say suppose there is a this is a flow pipeline. Obviously, I take the most general case there. Say suppose I point it out that this is the distance, the center of the pipe is a distance of h1, and here the liquid is flowing, and this is at a velocity of v1. The area of cross section is a1, and okay, this is a v1 and a1, and at this position the pressure is p1. So v1 is the velocity, a1 is the area, and p1 is the pressure. Similarly, at this point, this is section 1 and section 2, I say that this distance from the ground is h2, and here the cross section is different, so it is a2, and naturally the velocity will also be different, v2, and the pressure here is p2. Okay, I take the most general case there. So in between the flow is going from the bottom to top there, and we know that we have assumed the frictionless flow, that is a turbulent. So in that case, what we can say that this is a Bernoullis principle. What it says, it is the sum of the kinetic energy and the potential energy is always conserved if the friction is neglected. So we can say that this is a P1 by gamma plus of V1 square divided by 2G plus of H1 is equal to P2 by gamma plus V2 square divided by 2G plus of H2. What is gamma? Gamma is the specific weight, which is nothing but rho into G there. And I say that this is an incompressible fluid, so it's a liquid, the density remains same and this one. So this P1 gamma and H1 represents the potential energy, while V1 square by 2G represents the kinetic energy, and they are conserved if we neglect any friction in it. Okay. So we try to simplify that one. We say that if H1 is equal to H2, then it is P1 by gamma is a plus of V1 square divided by 2G is equal to P2 by gamma plus V2 square divided by 2G. And I can write that V2 square minus V1 square is equal to 2G by gamma into P1 minus P2. Okay? 2G V2 square minus V1 square is equal to 2G divided by gamma into P1 minus P2. And we know if for incompressible flow, what we can say is that V1 into A1 is equal to V2 into A2. Okay? Because that is the total flow rate is the same for the, that is the total volumetric flow rate remains the same at these two sections, and this is a liquid, so it is incompressible flow there. So what we can say is that V2 square into 1 minus V1 square divided by V2 square, or we can write it down directly, V1 minus V2 is equal to minus A2 square divided by A1 square is equal to 2G divided by gamma into P1 minus P2. Okay. Or I can say that V2 is equal to, what is it? Twice G by gamma. Okay, I will put it in this way. First put it as 1 divided by root over 1 minus A2 square by A1 square into root over twice G by gamma into P1 minus P2. And if I say that the flow rate Q is equal to A2 into V2, because Q is equal to volumetric flow rate, this I can say it is equal to A2 divided by 1 minus A2 square minus 1, A2 divided by square root of 1 minus A2 square by 1, A1 square divided by 2G gamma, 2G by gamma into P1 minus P2. Agreed? And one more step I can say that for a circular cross section, so we know A2 by A1 is equal to, we can say it is D2 square by T1 square. and we often call, that means that it is dependent upon the diameter, and if we say if d2 by d1, I call it beta, is denoted as beta, then what is the value of q is equal to a2 divided by 1 minus beta to the power 4 into root over 2g by gamma, that is basically 2 by rho into P1 minus P2. Agreed? So this is our very basic expression there. This is our very basic expression there. What does it say is that at this point there is a difference in the cross sectional area, and at this point if you measure the pressure P1 and at this point if you measure the pressure P2, that is the pressure difference, you measure it P1 minus P2, then what we call it, the flow, and we know the cross sectional areas or the beta or this ratio of this one, and also if you know the what is the density of the medium there, it is possible to estimate from Bernoullis principle that what is the value of the volumetric flow rate. So that is what is done in the case of obstruction type flow meter. All the obstruction type flow meter, the principle remains the same, that okay, create some obstruction in the flow path and measure the pressure difference created by due to this obstruction. And if we know that this pressure difference, if we can measure the pressure difference, because we know we can measure the pressure as well as the pressure difference using different diaphragm type techniques and other techniques also, and then you can, you knowing the density, you can find out the what is the flow rate, you can estimate this one there. And sometimes it is also expressed it, so it is in terms of liter per or meter cube per second, but sometimes it is also expressed in mass flow rate. Then you multiply it with the density, you will get it the in kg per second, or like this, what is here. But there is a small correction.
Sir,
Yes?
sir, here the obstruction is the height difference, right?
Pardon?
Here the obstruction which you are trying to create is being caused due to the height difference, right?
No, no, I have already assumed that H1 is equal to H2 for this
Okay.
case.
Okay,
So
okay.
it's basically the pipeline is horizontal, but the gap between, I
Right.
mean, the area is
Yes,
this.
sir. Yes. Yes, sir. Yes. Okay. Okay.
Is it okay? Any other question? So, from this one, I can say that the concept of what we call it, actually, we go to the actual construction of the flow meter. First of all, we go for the orifice type flow meter. What is there is that it is basically, you can see that I have considered a pipeline of non-uniform cross section, but the pipeline is horizontal. In fact, always you remember that this orifice plate is one of the simplest example of flow measurement. It's always the pipeline has to be horizontal. Otherwise, we need to incorporate some extra corrections and all other things there. So the orifice method, what we do is that This is known as orifice plate. Just a simple plate where the flow will be blocked the outside. Only the inside smaller circular area, it is open where it will allow flow to pass, but this will obstruct. The outside part is solid. It will obstruct the flow rate there. And this orifice really it is done in this way.
So last method will come in differential pressure or variable area, like you have told in the last class.
Pardon?
So the last method which we discussed is this is for differential pressure or variable area technique, which you told in
Yeah,
last class.
that's right. Very correct, you have said. This is the case where we are considering both differential pressure as well as variable area. Okay, this is the case, it is a area. But what I wanted to say is that why the differential pressure is created? Because of the area is varied. Why the differential pressure is created? Because the area is varied. So that is what we are trying to create a differential pressure by varying the area. But definitely making this sort of pipeline is difficult where it is changing. Rather we put some sort of uh, what we call it a obstruction, and this is known as orifice plate if you look at it. So this is a pipeline. So what we do is that this was a pipeline, and here in the pipeline I make a break. I just cut it and I insert a very thin orifice plate into it and then bolt it properly. So that obviously we need to ensure that there is no leakage there. So after bolting it, and the orifice plate is looking like this, and the construction of this one orifice is a very thin A there, uh, and it is made of some hard metal or steel or like this, but there are certain angles and these things there. You refer to Bentley's book or any other instrumentation book, refer to the what would be the pressure, what would be the actual constructions, what would be the dimension. Normally this angle is 45 degree, what is the this part and what is totally a. These are the other things. I am not going into detail. And normally we put some a there, tappings at these 2 points, and here it is a P1 is the pressure and P2 is the pressure there. And you can measure the pressure difference, or even you can put it in a manometer or like this there. And in this case, and where to put all the things are there are certain guidelines. This should, a common A is that there are many A there, that this is if the diameter is D, it should be at a distance d from the orifice, the tapping, and this should be at the distance of d by 2 there. So you put the orifice inside and you place and you put some tapping here measuring P1 and P2, and you try to measure difference, find out the difference between P1 and P2, and knowing, so this is possibly, I call it small d is the orifice diameter. So D is known, capital D is known, G is known, gamma is known, and A2 and beta are all known. So by measuring P1 minus P2, we can get the expression of the flow rate. We can find out like this there. Okay. So this is what we call it as an orifice type flow meter, which looks to be quite simple and very popular because of the low cost and this one. But definitely you must have to be there, careful there, that the pipeline has to be horizontal. Otherwise, you need to put some more factors because H1 and H2 are like this there to put it there. So, but I am, for the sake of simplicity, I am not considering this one there. Okay. Now, if we look into the flow pattern, we will see that the flow will be definitely, it was flowing to the pipeline, and after that it will contract, go like this, and then at the orifice it would be, the flow area will be small d, that one, and after that it will, flow profile will go like this one. So this is your flow profile. That means if you make some sort of color liquid there and the pipe is transparent, and put your try to see it in naked eye or something like this, you will find that suddenly the area is not, cannot change drastically. It will be a flow profile, will be a continuous one. It will start reducing in this way, and the again it is going back to the original one like this. And mind it, one thing is that we try to put the P1 and P2 tapping such that at this position, so it is at least d distance there. So the flow profile in this case, it caters, it covers the full pipeline diameter, and like this there. And but for doing P2, I put it d by 2, because if we see, the flow area is not minimum at this moment, but after certain time it goes like this, and then again flow profile area increases. And this is known as, vena contracta. Because these things are very old, a Latin name, because these were in 16th century, 15th century, or like this here. So, and this is named by the minimum flow area. So, this is a minimum flow area, and that is actually the flow pattern. So, why we try to put it that the tappings at a distance approximately d here and d by 2 here. Of course, it depends upon the design of the orifice, but approximately I am telling, and those details you can see it in Bentley's book or any other book. And the tapping P2 is, we try to place it around the vena contracta, where it is the minimum flow area there. I think the venium flow area, I think I will put it a slightly area, because I can do that one. Okay. So this is your vena contracta, where is the minimum area. But two things are there. From this expression, we need to incorporate some correction factor. We need some correction needed. What we do is that we multiply it. Q is equal to A2 divided by 1 minus beta to the power 4. Here I multiply it by CD, and there it is 2G by gamma into P1 minus P2T. What is CD? CD is a correction factor, and CD value is less than 1 and in between 0 to 1. And CD is known as discharge coefficient, which is actual flow by ideal flow. So it says that the actual flow is, so it is an overestimation of the flow rate. Actual flow is less than the ideal flow rate. So I will say it always actual flow rate and ideal flow rate. So why we need to incorporate the CD? Why we need to incorporate the CD? Okay. I think this part I can forget it. Why we need to incorporate this CD? Because there are 7 reasons. Number 1 is that frictionless flow assumption is not valid, because always there would be some friction there, but I have not considered at all the friction there. This is the thing there. And second thing is that minimum flow area is not the orifice area, because we have seen it that this orifice has a diameter d, small d, and the flow area is pi by 4 d square. But this minimum flow area is further a little bit away from the orifice, and which is less than that one. And we put our tapping not at the orifice, that's why, to get a larger A at the point P2, where the vena contracta is occurring there. So naturally, this flow area is further reduced, and the frictionless flow is there, and that is a important thing that will give you inaccuracy. To overcome that one, we need to incorporate a correction factor, and this correction factor is CD, is called the discharge coefficient. Yeah. And mind it, the CD cannot be that much exactly uh, calculated theoretically, because this has to be always normally best way to estimate CD is to carry out experimentation. Carry out the experimentation. So how do you measure the actual flow rate in that case? Okay, think of, I will come back this one. But what we can say is that this CD is a function of Reynolds number and our diameter of the orifice D. Or rather, I will put it in terms of beta. CD is a fraction of Reynolds number and beta, that is a D divided by capital D. So, we need to correct it, but at the same time, uh, it is not possible to exactly, unless you carry out experiment, exactly find out what is CD, but for the design purpose or like this here, we can, okay, let's give a break and then we'll come back after that.